So the idea is everything else will be the same. Let's say if you have a parallel circuit, you have series circuit, you know how to calculate, right? There will be a different equation for each of them. Alright. Okay, now we go to the next method. Okay, method to calculate heat transfer. Okay, so what we're gonna do is we're gonna apply what we call as a thermal resistance method. Okay, the concept of thermal resistance method is actually based on the equation of heat transfer. For example, conduction, convection, and radiation, you have the equation, right? But we try to simplify that equation into a thermal resistance method. Okay. Okay. The analogy of thermal resistance method is actually the same like when you calculate electrical current flow. Okay, as you can see here, you have a voltage, okay, V1 and V2. So in order for you to determine I, which is the, what is I? Current, okay, equals to V1 minus V2 divided by the resistance. Okay, so instead of this, which is the one that you familiar with, okay, the same you apply to the thermal or heat transfer. So now you have T1 minus T2. Okay, I mean for temperatures the same with voltage. For Q is actually the current, and for the R, resistance, thermal resistance, R is actually the same like your electrical resistance. So the idea is everything else will be the same. Let's say if you have a parallel circuit, you have series circuit, you know how to calculate, right? There will be a different equation for each of them. So I need to explain how basically we get the R. Okay, it's actually from the equation itself. So let's say we have a wall. Okay, thermal resistance network is you are going to represent this into something like this. So this is your T1 and this is your T2. Okay, so of course you know this will be linear, right? The direction of heat transfer. So since T1 is larger than T2, your Q from left to right. So here is your R, the resistance. Okay, and then you know that this is actually your, okay, I put this one as L, even though you know this one is thickness. So meaning the L is actually the thickness of the wall. Okay. So by equation of heat transfer of conduction, you know that Q equals to negative Ka T2 minus T1 divided by dx, right? Dx. So in our case, is dx is L. So here what you're gonna have is in the end you're gonna rearrange your equation becomes a positive value of Q. So Ka Ka T1 minus T2. Okay, T1 minus T2. And then divided by L. Okay, so everything become positive. So if you compare this one, the analogy of the thermal resistor method, okay, you compare this and this one, which this is also Q, right? So what you're gonna have is R equals to what? L divided by Ka. So that is R, which is I can put it here as R conduction. Yes, that's how you determine R for conduction. Okay, so let's say if you know the length of these problems and you know the thermal conductivity of this problem, so you can determine the R plus the area, okay, L divided by Ka, and with the area you can determine the R conduction. So everything else will be simplified into this. Q equals to T1 minus T2 divided by. Okay, so how about convection? Okay. So for convection, we have a wall. So we have your surface temperature, P surface, and then your ambient temperature. Okay. Okay, we always try to represent convection, not linear. There will be a curve there. So how we draw the resistance for this one? Okay, you're gonna start with the end of wall. So this will become T surface. From here to here, it's gonna become T infinity. Okay. So in between is your resistance. So you're gonna have your R there. So I can put it as R convection. Okay. So the equation of convection is Q equals to HA and then Ts minus T infinity. So again, you are going to compare this one and this. Okay, 1 over H. So that's how you calculate R convection. Okay. So you know H, and then you know area, then you can determine R convection. So let's say if this problem is calculated from inside temperature. So let's say we put this one as T1 and we change this one into T2. So T1 is larger than T2. So heat transfer is from the inside to the outside. Okay, T1, T2, and T infinity, right? So how you draw your network? Thermal resistance network is so this is your R conduction. Okay, and this one become your T1. This is become your T2. Okay, how about the Q? Q is equals to, okay, let's say the value given is only T1 and T infinity. So meaning this is T1 minus T infinity R conduction plus R convection. Okay, so this is how we determine the Q, which is, we can put it as the, I don't want you to get confused, is it total Q or not? I just simply put as Q. Okay, because of what? This Q also similar to this one. Q equals to T1 minus T2 divided by R conduction. Okay, this Q similar to this Q as well. See, let's say if you get this value is 20 watt. So this 20 watt also similar to T1 minus T2 divided by R conduction. Okay, also equals to T2 minus T infinity divided by R convection. Okay, so yeah, this is the beauty of it. If you get one Q, meaning it is actually valid for another one. The problem is do not get it wrong. Something like this. Okay, Q equals to T1 minus T infinity, but you didn't include one of them. Okay, T1, T infinity, you just include R conduction. So meaning wrong. Okay. So it should include overall resistance. Overall. Okay. So since our problem is in series, so meaning how to determine overall resistance, we just need to add up R conduction plus R convection. the same concept we're going to apply with radiation. Okay, so you will be given H radiation. Okay, so meaning in order for you to determine R for radiation is actually 1 over H radiation multiplied with area. So everything else, just now our equation, I mean, you know that our equation is Ts to the power of 4, right? So those power of 4, everything already been put into H radiation, being considered into H radiation. So H radiation will be given. So for radiation, can I use this as well? Okay, so let's say this is your radiation. Okay, so let's draw something like this. So this is become your radiation. So this is your T surrounding, and this is your TS. You know, right? They always draw radiation something like this. So instead of that, why not we put it something like that? Okay, so almost similar to the thermal resistance network. Okay, so you have your T surface, and then this is your T surrounding. So in between, you're gonna have your resistance. So this is for radiation. R radiation. Okay, so what you're gonna have is this is T1, TS, and then this is T surrounding. Okay. So how to determine this one is take a look at your radiation equation. You have Q equals to emissivity, sigma, and then area. And after that, you're gonna have your T surface to the power of 4 minus T surrounding to the power of 4. Okay, so compare this Q and that Q, right? So R is actually 1 over HA. Okay, but the thing is, this guy, this H is actually hash rate. So what is hash rate? Hash rate is everything else without the surface temperature and surrounding temperature, including the power of 4. So meaning hash rate will be given to it. Emissivity, sigma, area no lah, because area is here, and then Ts to the power of 4 now become Ts to the power of 1 because this is D, right? So this will become your Ts. This will become your T surrounding. You don't need to put to the power of 4 here because H already covered this one. That one. Okay, so Q rad, and this one also Q rad. Right? So in order for you to calculate R radiation, so this is R radiation, equals to 1 over hash rate multiplied with area. So that is how we consider on radiation for thermal resistant method.